As we're talking about conservation of linear momentum, let's continue with cases that explain collision, elastic and inelastic collisions. Now, we'll consider case 1. In case 1, let's assume that a body is m1 and is moving in this direction with an initial velocity u1. And another body is m2 and is moving with an initial velocity u2. But they are moving in the same direction. If they collide with each other, something will happen. The two of them will collide with each other, and when they collide and they move together in the same direction, this will be m1 and this is m2. But true, if this body is moving in this direction, this is moving in this direction, and they collide, this collision is inelastic. The reason is because they do not bounce out. They move together, they stick together to move in one direction. So this is what we call inelastic collision. Now, this happened before collision, and this happened after collision. So before collision, body m1 was moving with initial velocity u1, and body m2 moving with initial velocity u2. Then after collision, m1, m2 stick together because their collision was inelastic. So this is after collision. But the principle of conservation of linear momentum states that in a system of colliding bodies, the sum of the initial momentum must equal the sum of the final momentum. So because of that, initial momentum equal final momentum, provided no external force is applied. Now, what's the sum of the initial momentum? That's before collision. The momentum here is m1 u1 plus m2 u2. So this is the sum of the momentum. Initial momentum of this is m1 u1. The initial momentum of m2 is m2 u2. Momentum is mass times velocity. Okay. Is equal to the final. Now these two bodies are sticked together. So because they are sticked together, that is inelastic collision. They are sticked together. So you consider them as one, as an entity. So we'll have m1 plus m2. But this time they move with one common velocity, and that velocity is v, and that will be v. So sum of initial momentum is equals to the sum of the final momentum, which is m1 plus m2 into bracket v. Now, from this equation, from the equation, v can be calculated. Now, when you want to calculate v, you can calculate it from this expression. Sum of initial momentum equals to that of final momentum. Now, during the process of collision between mass m1 and mass m2 shown, there is a principle which states that in the course of transformation of energy, energy can neither be created nor destroyed, but can be transferred from one form to another. And in the course of transferring this energy from one form to another, there is always loss. It's never 100% efficient. So in the process of this collision, in between this space, there is loss of energy. And because these bodies are moving, the kind of energy they possess is called kinetic energy. So I can consider the loss in energy in this system. The loss of energy in this system is simple. Loss of energy, or you can call it energy change. For this first body, the energy it possessed initially was 1 over 2 m1 u1 squared. This second body also possesses 1 over 2 m2 u2 squared minus. Then this final system, that's after collision, possesses the energy 1 over 2 m1 plus m2 into bracket v squared. So that gives us something of this nature. What is common between these two? What is common is 1 over 2 is into bracket m1 u1 squared plus m2 u2 squared minus m1 plus m2 v squared. So that is the value of the loss of energy. Sum of initial energy minus sum of final energy will give you the loss of energy or energy change. Now, that is for case 1. Let's consider another case. For case 2, class, case 2, a system of colliding bodies. Let's consider a body, M1, moving with U1, and another body, M2, but moving in opposite direction, U2. So M1 is moving in this direction, while M2 is moving in the opposite direction. In the first case we considered, M1 was moving in the same direction as M2. But in case 2, M1 is moving in an opposite direction to M2, and M2 in an opposite direction to M1. Now, this was before collision. Now, when the two of them collided, they stick together or changes direction. They stick together or can change direction. Now you have M1 V1, M2 V2. Now, this is after collision. Now, take a look at it. M1 was moving in this direction, but when it collided with M2, it changes its direction. And M2 was moving in an opposite direction to M1, but when they collided, it moved in the other side. Now look at it. Initial momentum is equals to final momentum. Let's see the sum of the first here. You have M1 U1 plus M2, you have U2 is equal to, in this case, you have M1 minus V1 plus M2 minus V2. And someone asks, question, where did the negative sign come from? The negative sign comes from the fact that after the collision, they respectively change their direction. So the change in that direction will give the value of minus. So when their direction change, negative sign is applied. So here, this is the direction of M1, but here look at its direction, it's the opposite. So the sign will change. So same apply to M2. So the direction change, so it becomes minus V. Now, from here, we can have M1, U1 plus M2, U2 is equal to minus M1, V1 minus M2, V2. So that gives us the value M1, U1 plus M2, U2 plus M1, V1 plus M2, V2 equals to 0. So you consider this as the second case. So we've talked about case 1, we've talked about case 2, and you can consider the energy loss in any of this system by considering the energy of this minus, add them together and subtract the energy of this. So you get the energy loss or energy change, just as in case 1. Now, let's consider a common case, which is case that you are used to. You see questions in that particular case. I'm taking that as last because it's case 3. Now take a look at this class. Case 3. This case is when a body M1 is moving with an initial velocity U1, collides with another body M2, but the M2 has a problem. The problem with M2 is that M2 is not moving, it's stationary. M1 is moving, but M2 is not moving. If M1 collides with M2, which is not moving, meaning it's stationary. So if it's stationary, the value of U2 is equals to 0, meaning the body is not moving. It has no initial velocity. Good. Now, this is before collision. This is before collision. So after collision, what happens? If these two bodies now stick together, it's a common case. If these two bodies now stick together, you still have M1 and you have M2. If these two bodies stick together, they will move with a common velocity. Now, this is after collision. So after collision, initially, what do we have? We have M1, U1 plus M2, U2. Please don't forget that U2 has a value of 0. It's equal to M1 plus M2. The reason is because they are now considered as one because they stick together. This kind of collision is inelastic collision because they did not separate. Unlike case 2, where they separated, that is elastic collision. Now, from here we'll consider V. So from here, if this value here is 0, so that will make it M1, U1 plus M2 into bracket 0, M1 plus M2 into bracket V. So because of that, M1, U1 is equals to M1 plus M2 into bracket V. So from here, V can be calculated. And the value of loss of energy can be obtained from the energy of this minus the energy of this. So from here, we've understood how collision, elastic, inelastic, and 3 different cases have been considered. Now, we are going to take a few questions to explain calculations that has to do with conservation of linear momentum and Newton's laws of motion in general. Now, from the examples, let's consider example 1, first of all, on Newton's laws of motion and conservation of linear momentum. Now, from example 1, we will take this, a bullet of mass. A bullet of mass. This is the mass of the bullet. You mark it out. It's my usual way of solving questions. So this value here is mass of bullets. So automatically your mass of bullet is 0.045 kg. That's the value. It said is fired from a gun of mass 9 kg. So the mass of the gun is 9 kg. So I can pick that. Mass of gun is 9 kg. Okay? It said the bullet moving with an initial velocity of 200 meters per second. Surely the bullet will be faster than the gun. So the velocity of the bullet, VB, is 200 meters per second. Then the question comes in. Find the recoil velocity of the gun. Find the recoil velocity of the gun. Now, we know very well that the recoil velocity of the gun is the velocity of the gun. Now, from our deductions, you recall that mass of gun, velocity of gun is equals to mass of bullets, velocity of bullets. So velocity of gun is what we're looking for. That will become mass of gun, velocity of mass of bullet, velocity of bullet divided by mass of gun. So taking this out now, velocity of gun is equal to the mass of the gun of the bullets is 0.045. The velocity of the bullet is 200 meters per second, and the mass of the gun is 9. So from here we have 1 0 taken out, another, that's 2, that's 4.5 times 2 over 9, which is equals to 9 over 9. Therefore, velocity of gun is equals to 1 meter per second square. That's that. So from this value, we have V is equals to, which is the answer to that question. Now, you can take it again. Mass of bullet is this. Mass of gun is this. Velocity of bullet is 200 meters per second. And the velocity of gun is what we need, which is also called the recoil velocity. So, the formula remains: mass of gun, velocity of gun is mass of bullet, velocity of bullet. Velocity of gun is mass of bullet, velocity of bullet divided by mass of gun. And that gives us 0.045 times. You have that. 4.5299, and that will give you 1 meter per second square. Good. Now we'll proceed to question 2. So example 2 will be a car of mass 800 kg. The mass of the car is 800 kg. Traveling at 20 meters per second, is brought to rest by brakes in 100 meters. It said calculate the average braking force required. Good. Now, you recall that force is ma, mass times acceleration. From your question, you already get it that the mass of the body is known, but the acceleration of the body is not known. So how do I find the acceleration? Then that takes us back to equations of motion. Equation of motion will help you get the value of A, which is acceleration. Now take a look at it. Acceleration of the body is not known. The velocity said a car starts from a car of mass that is traveling at this is brought to rest. Immediately the car is brought to rest, then the value of V is automatically is brought to rest, the value of V is 0. And the value of U is 20 meters per second. So it's brought to rest that and brakes is applied in 100 meters. So the distance is 100 meters. So if you look at these three statements, which of the equation of motion can be used to find the value of A? It's simple. It is V squared is equals to U squared plus 2AS. So from this equation, it's easy. We know very well that V is 0. So from there, you replace the value of V as 0. That's 0 squared. 0 squared will give us the value of U is 20 squared plus 2. Now, the body is brought to rest. Because the body is brought to rest, we have the value as minus A. That is deceleration, not acceleration. The body is coming to rest. It's decelerating. It's not accelerating. So the value of A is going to be minus. So S is 100, which is 100 meters. So from here, I can take my values in raw calculation. So 20 squared will be 400. Is equal to, will be 400, and you have 0. You have 0 is equals to 400 minus 200A, meaning 2 times minus A is minus 2A, minus 2A times 100 is minus 200A. Now you collect like terms. If you move this guy across, it becomes 200A is equals to 400. If I divide it by 200, I divide it by 200. This will cancel this. So A will be 2020. 4 divided by 2, that will be 2 meters per second squared. That's the value of the acceleration. So the question said, calculate the average braking force required. The average braking force, F is equals to MA. M is given as 800. A is given, obtained to be 2. So 2 times it, that's 1,600 Newton. That is the value of the average braking force required to bring the body to rest. Now, we'll take one more question on linear conservation. Now, to the third question on Newton's laws of motion. A ball of mass 0.2 kg traveling with velocity of 100 meters per second collides with another ball of mass 0.8 kg moving at 500 meters per second in the same direction. If they stick together, what will be their common velocity? We have to write them out the way we describe them in our cases. Now, first, a ball of mass, this. Let's assume this is the ball. 0.2 kg. That's the ball. It was moving, or was traveling with 100 meters per second. Collides with another ball of mass, 0.8. This one was 0.8 kg, but it was moving at 50 meters per second in the same direction. Oh, they were going the same direction. So this is 50 meters per second. 0.2 kg moving at 100 meters per second collides with another ball of mass 0.8 kg moving at 50 meters per second in the same direction. If they stick together, class, that shows that it is an inelastic collision. So if they stick together, what will be their common velocity? If they stick together, that's after collision. So when they stick together, you have something like this, meaning they now have a common velocity. So this still remains 0.2 kg and this still remains 0.8 kg. Now, this is after collision, before collision. But don't forget, the sum of the initial momentum must equal the sum of the final momentum. So the initial momentum, let's pick them out. So that will be momentum, remember, is mass times velocity. So we'll take it 0.2 times 100 plus, for this is 0.8 times 50. Sum of the initial is equals to final. For final now you have 0.2 plus 0.8 because they are not considered as one entity. So you take that V. Good. From here, 0.2 times 100, that will be 20, plus, if you take this, 0 will take 1 forward, that's 8. 8 times 5, that will give us 40. So that will be 40. Which is equal to 0.2 plus 0.8, that will be 1. So 20 plus 40, that will give us 60, is equal to V. So therefore, V is 60 meter per second. So put that down. That will be our last question on Newton's laws of motion. It has been a wonderful time with you, and you can always go back and check from the beginning of the class, and I'm very sure that any question that you want to ask is always available in due course of the lectures. Thank you very much.